Welcome to this lecture number 15 of the course Computational Hydraulics. We are in module 2 numerical methods. In this particular lecture I will be covering unit 11 finite volume method initial boundary value problem. Learning objectives or objective for this particular unit. At the end of this particular unit, students will be able to derive the algebraic form for a initial boundary value problem using finite volume method. Let us consider our general equation in terms of general variable phi. We have solved the boundary value problem or BVP using this diffusive term and sourcing term. Now, in this particular lecture, we will be introducing this temporal term for IBVP problem. Now, what is this problem definition? Like our finite difference case, let us consider this lambda phi as coefficient for this temporal term and gamma x, gamma y, these are diffusion coefficients. So, gamma this tensor, this is basically 2 dimensional 0 0 gamma y. So, we have only 2 terms. If we write this in terms of this del or divergence operator, we can write this one in terms of this. This is basically del phi or grad phi. This is equals to phi I, where I is the unit vector in direction x, j is the unit vector in the direction y, and divergence of this this will give you the other terms. Now, what are the boundary conditions or initial conditions? Initial conditions, let us say that initial value is specified for x y domain or omega domain. For this one, for all values of x and y, this phi naught is given. Left hand side, like our previous problem, it is a specified boundary or Dirichlet kind of boundary condition. Right hand side also Dirichlet kind of boundary condition. Bottom and top boundary, these are Neumann boundary conditions. Now, domain discretization, like our boundary value problem, we can divide this Lx in x direction and Ly in y direction in number of cells. At the cell center, we will consider the variables, and in this case blue ones are interior cells. For representative one, this black ones are next to boundary, and red ones, these needs spatial treatment because one side is Dirichlet, another side is Neumann. in physical system there can be situations where both the boundaries can be Neumann or Dirichlet, but in this case we have combination of boundary conditions, one side Dirichlet, another side Neumann, and del x is a cell size on the x direction, del y in the y direction. So, with this we can start the discretization of the governing equation. If we consider any interior cell, then for any particular interior cell we have east, west, north, south, these 4 neighboring cells. For this one we can start the discretization. So, in finite volume method the governing equation is integrated over the elemental volume in space and time interval to form the discretized governing equation at node point P or cell center P. So, in this case we are integrating from t to t plus delta t, that is the time increment from present level t to future time level t plus delta t, and integration omega p, this is over elemental volume or element volume, this is actually element volume. So, if we integrate our original equation with respect to space and time, then we can write like this. This is for temporal term, spatial diffusion term and sourcing term. Now, let us consider the discretization for individual terms. In the first case we have this temporal term. This quantity is not varying with time. Let us consider this is constant. So, we can take out this term out of this integration. So, we can write this term, the spatial derivative, spatial integration with respect to temporal derivative. We can take this integration sign inside and let us integrate this phi over this element volume. With this, in the next step we can approximate this. This approximation is nothing but this phi p is the approximated value for this domain. If we consider this spatial averaging. So, this is actually spatially averaged value within this P cell. Now, let us integrate it from t to t plus delta t. So, if we do that, then we can write this one to this del p, this phi p L plus 1 minus phi L. L represents the t time level and L plus 1 represents t plus delta t time level, and this one is nothing but the volume of the cell P. Next step, we can simply write this is del x into del y, and virtually on the other direction we can consider the width as 1. So, this del omega p or volume we can directly write as del x del y into 1. Now, let us see the integration of the spatial or diffusive term. Spatial term, we can write this quantity in terms of vector like this. Now, in the next step, if we see this one, this is divergence of this vector. As per Gauss divergence theorem, if we have divergence of any vector A, then we can write it in terms of surface integral. So, in this case we can first divide it into two parts. One is t plus theta delta t, this is intermediate time level, and from t plus theta delta t to t plus delta t. Like our theta scheme in finite difference, this is intermediate time level, this is basically 0 level, this is theta, and this is basically 0 level, this is theta, this is 1, this is t plus del t, t plus delta theta, and t only. So, in this case if we consider this one, we can use the Gauss divergence theorem, and from Gauss divergence theorem we can simply write it in terms of this step. Intermediate step will be there. That intermediate step is actually t plus theta delta t, and this will be over SP or surface, and only gamma x del phi del x I plus gamma y del phi del y j dot n cap into ds. This is for first term. Similarly, we can write the other term t plus theta delta t, no, this is t plus delta t, and again spatial derivative for this one, this is for delta t and SP, that is for surface around P. So, in this case we can see that in this unit vector is always outward positive. Outward positive means for any case, if we consider for our cell P in east phase outward positive normal is in the direction positive I. In our west phase we have this negative I direction, north phase I have positive J, and south phase I have negative J. So, these are the direction for outward normal. Individually we can consider this effect. So, projected area in that direction is actually AXE. So, for east phase I dot this AXE, this is positive, is considered. So, if you multiply this only I dot I, that term will be 1, there will be no Y related term. Similarly, if we consider west phase, this negative sign will be there, north phase positive sign, and south phase there will be again negative sign, and this theta delta t, this is basically value for this first integral, and 1 minus theta delta t, which is basically t plus delta t minus our t plus theta delta t. This is nothing but 1 minus theta delta t. So, we have two different levels. At the present level, we have this Lth level, and future we have L plus 1 level. So, with these two levels we have expanded this space integrals, and we have averaged it for this time interval. So, for two different time intervals, initial one t2 t plus theta delta t, and next one is t plus theta delta t to t plus delta t, we have this multiplication. So, with this, if we proceed for further discretization in uniform grid system, we can say that for our uniform grid system, this is our P cell, this is east, west, and this is our east phase. So, for east phase P E minus P this phi E minus phi P, this is at Lth level because time level is L. For L plus 1 level, again we can write the same discretization for L plus 1 time level, and similarly we can write for west phase, where phi p minus phi w is required, north phase phi n minus phi p, south phase phi p minus phi s is required. So, if we substitute these values within our original governing equation, we can get the discretized form. In uniform grid, we can consider that area for east face, this is our P, this is east face, this is west face, south and north. AXE magnitude is del y and AYN magnitude is del x. So, now we need to see what is this source term. Source term, we can write it as average of present time level value and future time level value with weights theta delta t and 1 minus theta delta t, and combined manner we can write like this. Now, let us utilize all this discretized form to get the final discretized form of our governing equation. In the left hand side, we have lambda phi p L plus 1 L del x del y for volume of phi the omega p or element p. Now, for east and west phase, we have theta delta t, like north and south phase we have theta delta t, east and west phase 1 minus theta delta t, north and south phase 1 minus theta delta t. So, with this, if we divide both sides with and let us discretize substitute the individual values of these derivatives. So, with the spatial derivative evaluated at present time level for this 4 and future time level for this box form. Now, we can rearrange this thing with the consideration that gamma x e equals to gamma x w equals to gamma x and gamma y n equals to gamma y s equals to gamma y. Now, with this and dividing both sides with delta x, delta y and delta t, we can write this left hand side. This is similar to our finite difference discretization for any arbitrary node I j. In this case, we have cell center P L plus 1 to L, and further as per our assumption, we can consider these values equal, these values equal. So, we can combine north, south, east, west terms with this. If we combine this east west term, then this is basically phi e evaluated at lth time step minus 2 phi p plus phi w into del theta, and north minus 2 phi p plus s. This is evaluated for south cell. So, theta and 1 minus theta, these two weightings are weighted combinations are there, and theta minus 1 minus theta. Now, if we consider explicit scheme, then we can consider theta equals to 1, and then the L plus 1 level is 0, theta equals to 0, then we have implicit scheme, only L plus 1 level values are there for spatial derivative, and if we consider theta equals to half, we will have combination of L and L plus 1 level values, and I have transferred this half to the right hand side. So, this 2 is multiplied here. Now, up to this discretization IBVP is somewhat similar to finite difference discretization. Now, we need to see what will be the boundary conditions. Left boundary, again we need to evaluate this waste phase derivative separately, which is not common, and right boundary also we need to evaluate the derivative at east boundary separately. For north also this north boundary derivative of phi with respect to n or with respect to y, that will be 0. Similarly, for south boundary or bottom boundary at this south face, derivative of phi with respect to y, that will be 0. Corners, west side we need to evaluate the derivative separately, north side the derivative will be 0. This northeast, again east face derivative, north face derivative is 0. Southwest and southeast, similarly we can impose the corner boundary conditions. So, with these discretizations which are similar to your boundary value problem, we can get the discretized form of all the cell center points, and we can solve the final matrix and get the value for all cell centered values for all cell centered positions. If you have Dirichlet boundary, your boundary values are specified for, but for Neumann boundary we can utilize the nodes or cell centers next to our boundary to get information about the value at the boundary itself. Thank you.